Should I try to test it now?
Oh, it's actually okay.
Yeah.
Seems to be okay.
Okay, good. Yeah, big.
Resume recording. Yep. And so if you would not like to appear in the recording, kindly turn your camera off, please. So my name is Zach Shwirab-Conti, and I'm a research associate. Well, actually, I'm now a Turing research fellow at the Alan Turing Institute in London. I would also like to introduce my colleague and co-organizer of this seminar series, Davor Dundovic, who is a PhD enrichment student here at the Turing. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. Also, on a side note, if any of you are interested in sharing your work in any of our upcoming seminars, please feel free to reach out to us. So as for the format of the seminar, our speaker today, Alice, will talk for around 45 minutes or so, and followed by a Q&A session. So the questions may be asked in person by raising a hand, or can be typed out in the chat function, and I can relay those to Alice. So without further ado, I'll introduce Alice Cicirello today, who is our speaker. So Alice is a visiting fellow in the Department of Engineering Science and the University of Oxford, and also an associate professor and head of the section of Mechanics and Physics of Structures and Engineering Structures department at the TU Delft. Alice also leads the Data, Vibration and Uncertainty group. So previously she was a departmental lecturer in Dynamics and Vibration at Oxford Engineering Science department, focusing on solid mechanics and material engineering group, and a career development fellow in engineering science at the Balliol College. Prior to these positions, she was a senior research scientist at Schlumberger, a research associate and Marie Curie fellow at the Cambridge University engineering department. And finally, she also obtained her PhD from the University of Cambridge in 2013 and has held various visiting positions across institutions like MIT, Sandia National Laboratories, and also the University of Auckland. So after that very long bio, I'd like to introduce Alice, and you may take the floor. Thank you.
Thank you so much, Zach. I didn't thought that you were going to read everything, really. Thank you so much for doing that. So it's really my great pleasure to be here and an honor to be part of this excellent seminar series. And today the topic is going to be physics enhancing machine learning strategy in applied solid mechanics. And I'm Italian, and you can tell that by the way that I'm going to move my hands, but also I'm going to move because I have a standing desk, so you will see me moving. Apologies for that. I will look like a pendulum at some point. Before starting, I should emphasize that this is, of course, coming from the research of the group, and it's my research group, the people in the data vibration and uncertainty group, and especially some of the part of the work that I'm going to describe are coming from the work done with Luca Marino and Christo. So without further ado, I'm going to start. So the first slide should be already a disclaimer. I'm talking about physics enhancing machine learning in applied solid mechanics, but of course, this talk cannot cover everything. So this will be a part of the talk, and it will be my bias view. And to explain you my bias view, I should tell you how I see research and what are we trying to achieve within our research group. So basically, in a nutshell, we are interested in structure that are subject to a broadband type of loading and are subject to uncertainties and nonlinearity and various operating conditions. And for this structure, we use different models that have different fidelity, and we collect data, and we also collect other type of information from inspection report or failure report. And then what I'm very interested and passionate about are actually three engineering ground challenges, and this is what we focus in the group. The first one is how do we design complex structure, take into account uncertainties and nonlinearity. The second one is about monitoring this structure to assess the remaining useful life under uncertainty, nonlinearity, but also the fact that we might have noisy data. And of course, if we want to use machine learning to their most powerful, then what we have to do is to develop techniques that are explainable and interpretable that then can be directly used in engineering application. And In order to tackle these frequent challenges within the group, we actually have an integrated approach, and it goes from fundamental to physics in for machine learning. So what it means is that we carry out laboratory experiments, we develop physics-based model, we develop technique for information extraction and techniques for learning from measurements, models, and data, and also we account for uncertainty quantification. We develop technique for that. The overall goal is to guide in decision-making at the design stage and operating condition. More specifically, what we're trying to do and what we are aiming to do, and this is our research vision, is to predict the performance of innovative design. It is to assess the remaining useful life and is extracting and integrating the most useful and accurate information. So I'm talking to you about an integrated approach, but why do we need it? Why it is so important when we talk about physics for machine learning? Well, if you think about solid mechanics in general and apply solid mechanics, we have some challenges when we are interested in modeling and forecasting of the dynamics of multi-physical and multi-scale system. And on these slides, to the left, you see some of these challenges: multi-fidelity models, image generation, high dimensionality, computational cost. But of course, there are other challenges that we are well aware. The fact that we might have, we might want to integrate heterogeneous information and domain knowledge, and we also have to deal with uncertainties. The fact that we don't know precisely every single information that is coming in or every detail of our model. But an integrated approach is also needed when we do the inverse, when we look at the measurements and we want to build better model or characterize better our inputs to the model to then assess the behavior of structures. And when we think about these challenges, we have to deal on non-physical parameters. Maybe we don't know precisely the physical law. We have gappy and noisy data, and we may know partially only the governing equation of the problem. But of course, there are other challenges, and that's, again, why we need an integrated approach, because we have to deal also with multi-fidelity data, confounding influence affecting our results, but also high-dimensional problems, computational cost, and you can guess uncertainties is coming back in. Okay, are these only the challenges? Is it this why we need an integrated approach? Actually, the reason why we need physics for machine learning and an integrated approach is that in order to support decision-making in applied solid mechanics, we need to go beyond what are the black boxes approaches. And we need to have something that is both interpretable and explainable. What do I mean by that? Interpreters try to answer the question, how was a prediction made? Explainable instead focus on how can we communicate the prediction to support decision-making. While interpretability focus on can we understand if the model succeed or fail, and then it's important because we want to build trust. In explainability, we want to make sure that our prediction, our model are actually, and the results are comprehensible, and we are able to quantify any remaining uncertainties. And of course, the main challenge there is that these results must be understandable by humans. Humans are the ones that have to take decisions. So they have to trust these results and they should be able to understand. And these are very important for guiding decision-making. Okay, but we know that machine learning is actually quite widely applied in solid mechanics. And in fact, we have had recently fantastic results in terms of extracting information, improving modeling and forecasting, and reducing computational costs. And many researchers have been developing excellent techniques for engineering feature extraction, classification of health status, but also statistical model updating, virtual sensing, transfer learning, and also in the reduced computational cost area in terms of building surrogate models, but also efficient uncertainty propagation. So if machine learning is so powerful, why do we need physics? Why so important an integrated approach? And why do we need to account for physics as much as possible? The best way I can think of explaining this, and I really hope to hear your feedback about it, is to think about this sort of two-dimensional graph, in which to the right, in the bottom axis, you see physics knowledge, while into the y-axis, you see informative data availability. It's not just all the data. This data should carry some information. And what we can do is that we can divide this graph in these 9 areas, in which we have low, medium, and high physics knowledge, and low, medium, and high informative data availability. What you can immediately think is that if you have very little knowledge, but you have lots of informative data, then machine learning might be the best option. And of course, if you have very, very little data, then you might rely on your physics knowledge. Everything in between is actually physics for machine learning. So we really need to be careful about the level of information that we have, the physical knowledge that we have, because most of the time we actually fall into this graph, into this physics-informed machine learning. And why it is so important to account for physics? Because usually the volume of experimental data that we have in engineering structure and applied mechanics is actually relatively small. And the other information that sometimes is sort of key information that is missing is that if we want to use those models generated by data-driven technique in small to medium, in the small to medium data regime, we want to also enforce some physics, some constraint. So every time we think about machine learning, even in this condition, we should take it with a warning. And the warning is twofold. First of all, we have to be careful because a purely data-driven approach might lead to poor generalization performance. We might basically have extrapolation or observational biases. But also, this might lead to physically inconsistent or implausible prediction. And what I mean by that, basically, we have to always remember that we are dealing with real measurements taken on engineering structure, engineering system, and therefore we might have corrupted or non-informative measurements. We may have basically, with data-driven technique, might get back some correlation and associational evidence, but not necessarily a causal relationship. Or we are not most of the time in a position to distinguish which are the many sources that are causing an effect. As a result of that, we have to be careful, again, with using data-driven techniques, because we might get very accurate but wrong prediction. And again, this is why it is so key to incorporate physics knowledge, and why physics-informed machine learning, physics-enhanced machine learning, scientific machine learning, whatever you want to call it, actually is so key and so important in engineering. So then this lies back the question, how do we actually incorporate physics to enhance machine learning strategies? And there are actually 4 approaches that are widely used. The first one is to think, okay, we want to induce some biases in the data. So we want to generate maybe data with our model because we know that we want to have certain behavior that are included in our data set. This is one way in which we can include physics behavior. Another way is considering inductive biases. So basically, we might have prior assumption on symmetries, boundaries, conservation law, and basically we can induce these biases into our algorithm. Another way to look at this, how we can incorporate physics, is to consider learning biases or better training biases, in which basically the way in which you build our system loss function, optimization constraints, all the algorithm are actually devoted towards going back to the physics information that we have. And we can also think about another bias, another way to incorporate physics, that is actually consider that we might have partial physics knowledge. So we might have terms, equation, we might have some information about the physics. And therefore, we would like to account for these sort of discrepancy biases on partially non-physics-based model. And of course, this is a sort of general framework. And the idea is that in principle, we can combine all of these together in one algorithm, or we can take some of these parts, depending on the information that we have, the availability of data, of course, but also on the kind of framework that we are using. Ideally, combining all of this will help us accelerate training, but also enhance generalization, and therefore having a better model. Okay, so the best way in which I can think to explain this with a very quick example with no equation is actually to look at a neural network. So let's imagine that we have a neural network architecture in which we have an input layers, we have some hidden layers, and we have one output layer. Now, our goal is to actually identify a partial differential equation. And what we can do is to actually then introduce some operators, constraints, and then we can have some partially non-governing equation. And what we can look at is actually the difference between the results obtained at the output layer and the governing equation, define and choose a loss function, and then decide if we actually have to go through the architecture again, or we have to make changes, or if you are happy with it, depending if it satisfies certain limits, certain constraints. So what you can see here is very easily a way in which we can incorporate all of the biases that I described before. The observational biases can be one node, for instance, of your artificial neural network at the input layer. We might have inductive biases in the way we actually shape the architecture and we set up some constraints. We might have also learning biases that come from how do we choose the loss function and actually the constraints and how we perform the inferences. But also we might have discrepancy bias in terms of the things that we assume that we know and the things that we say we don't know and we want to learn them. And they come from the partially non-governing equation. So I hope that this gives you the sort of overview of where physics can come in. But then again, when I was preparing these slides, then all of these slides were begging the next question. And I hope that this is also the question you have in your mind. And it is, okay, but then we were talking about an integration challenge. But what we are describing actually goes almost beyond data and mathematical models. And in fact, it is, because it's not just the mathematical models and the data that we have, but actually come from the fact that we're going to have multi-fidelity data. We might deal with non-informative data and corrupted data. We have domain knowledge and prior knowledge and other biases that might be appropriate that we want to incorporate. But we also want to have our result to be interpretable and explainable and account for uncertainties. So physics-informed machine learning goes and try to encapsulate, in my opinion, this integration challenge of having all of these requirements there and helping us in a way to basically then make a more accurate prediction that are more generalizable. But how do we do this? How can we do it? Well, the answer is the usual answer probably in every engineering field, that there is no one size fits all. There's nothing that is brilliant and work all the time. Pins is great, but it might not be the right tool for certain application. And in fact, it depends really on the complexity of the system that you're investigating, on the amount of informative data of information, but also the purpose. What are you trying to achieve? So what I'm trying to do in the next slides is to summarize 4 main paths in which I can see that then we can formulate physics-informed machine learning. And after that, I'm going to talk about the recent advances within the group. Okay, so the 4 main paths. So the disclaimer is always there. It's biased towards applied mechanics and is biased towards the things that I'm mostly interested about. So there are many more paths, but these are the ones that I'm very interested in. So the first path is focusing on learning a non-physics terms a question. And you can think of having some interpretable, observable variables, and you want to go from these interpretable observables to learning this equation. So how do we do that? We might collect some noisy data. We might formulate a dictionary of operators that account for the physics that we know. And then we can apply some learning algorithm with or without physics constraints. This is a sort of general framework that might resonate with you for 2 approaches, for example, or even more. One is physics-informed neural networks, but the other one is also the sparse identification strategy, in which you can think of having an equation and a no functional form. And what you're trying to do is to use a dictionary of operators to actually then being able to evaluate these unknown functional forms from measurements. But of course, we want to include physics. And where the physics coming in is, of course, in the selection of this dictionary of operators, but also we might want to include explicitly some constraints. And you can see at the bottom some references about some of the topic I put in generally the lead scientist and the group because there are many papers and many excellent works being done by these people. The second strategy, the second path is learning useful information or reduced order models. And what happened is now we have some data, some observation, and we want to get there. So how do we do this? We might apply some manifold learning, so autoencoders, to determine a reduced latency pairs and then learn these rules. And if you think about it, this is actually what is happening when we have the autoencoder structure, in which we have some input layers and we want to go into a latent space that is much smaller. And we want to then go back into an output layer that is a physical layer. And if we are into this code layer, basically, we are able to reduce the problem and then to work out into this problem. And again, at the bottom left, you will see some of the names of the people leading in the field. And I would strongly recommend you to look into the research outputs of these colleagues. Another path that is quite interesting is quantify uncertainties in the parameters. But we are assuming that we have a very well-known physics-based model. So we know a physics model, and now everything that we don't know is actually in the uncertainty in the parameters. And in that case, we still collect noisy data, and we still apply learning algorithm with or without physics constraints in it. The physics is coming from having a physics-based model already embedded. And the way to do this is actually, as an example, there are many more, is statistical machine learning strategies, in which basically we have a likelihood, what you see on the right, that is coming from the discrepancy between what we observed from the data and the model prediction. And what we have on the left, there is a prior distribution. There is our prior knowledge of things that cannot be directly observed. And so they are latent because we cannot directly observe this variable, and we want to update our knowledge on that. And the idea there is to develop and to be able to determine a posterior. And to do that, the challenge is that, of course, the computational cost, but also the informativeness in the data. And again, at the bottom, you can see some of the names of the people working in this area. And then there is the fourth path, and it's actually quantify uncertainties in the parameters terms of partially non-physics-based model. And basically, the idea is that you have a partially non-physics model, but you don't know the functional form. It is uncertain. There is a lack of knowledge. You don't know what it is. And there you can have, again, noisy data, and you want to apply some learning algorithm with physics constraints. One example is the Gaussian process latent force model, but also some physics-enhanced sparse identification, in which basically you want to combine something that you know, that you want to use as a bias with something that you don't know. And the way in which you actually determine something that you don't know might be dependent on the problem. And especially for these last two problems for path 4, I'm gonna give you some ideas of what we've been doing within the group, although we touch upon many of the other paths, but there will be no time to go through all of them. I can already see Zach being nervous about me talking for 4 hours, and I could. So let's move on then to the fact that, as I told you, there is a big disclaimer. This is a bias view. And of course, there are even more paths, but there are even more challenges in physics-enhanced machine learning in applied solid mechanics. And here, what I'm trying to give you as a disclaimer is that this is my view on it. And so many of these challenges come down to incorporating multiple physics models, explainability, interpretability, visualization of the results. How do you transform between predictive models, but also a big word. If you use a physics-informed machine learning algorithm or another with the same training data, we may get different performance. And this is worrying, and this is actually telling us, again, that there is no one size fits all, and we have to figure out also well to cross-validate or to understand which are the things that will lead us to a better model, depending on the application. And of course, the other problem is scalable solution for complex problem. And I can go back all the time to quantifying uncertainties, because this is one of the key issues that we are facing all the time. But of course, we don't have to forget that all of this is great and it's very relevant, but physics model and physical understanding will remain there. In engineering, to have a causal relationship, to learn something that is physics-based, we still have to improve physics model. So we cannot get away just with data-driven techniques or data-driven tricks, let me call them this way. We really have to understand the physics. And during the second part of this talk, after this general introduction, I really hope to convince you why it is so important to really understand physics. Okay, so now I have to basically start diving into the technical work. I promise there will be only few questions reference to the papers, and I will be very happy to discuss in very much detail every slide that has been presented so far, but also that is going to be presented shortly. So I'm going to focus on one topic, and the topic is friction. And friction is the force resisting the relative motion of surfaces sliding against each other. And friction is so important in engineering because it's present everywhere, pretty much. Every time you have a joint, every time, even when you walk, it's because of friction. So what happens is that there are so many advantages, but also some disadvantages of having friction. Of course, the advantage is dissipating energy and reducing vibration amplitude, but there are the disadvantages that come from noise, large oscillation, and also this stick-slip behavior. You will learn about it in a few slides. And all of these problems may lead to a reduction of the remaining useful life of a structure and sudden failure. And there are different examples of structure when I'm talking about. This is not relevant just to wind turbine, to engine, to structure, but it is in general in many different types of connection. The key thing is that in none of these applications, you can directly measure friction without affecting the relative motion. So this is why we really need an integrated approach that combines what we know, what we don't know, and they collected somewhere else. So how does it work? So this is actually a work that started a long time ago and has been done in collaboration with Luca Marino. He started during his PhD, that started in 2018. And during also his postdoc, we continued working together on this. And the main idea is that we would like to learn something. So we have a failure in engineering structure, and this failure might be caused because there's a problem with the contact. And the thing was that the contact that we have there is a friction contact. And we started thinking, do we understand truly what is happening at the friction contact from the physics point of view, not even thinking about machine learning at that point. And we realized that there was so much that we didn't know from the physics point of view and without that knowledge, we could not go from the fundamentals to the physics for machine learning that actually can predict the friction. So during this second part of the talk, I will explain to you what we learn, how we use it, and also how we use it to predict the friction force without directly affecting the contact. So the complex problem, as I was mentioning to you, was this unexpected failure that were happening at the after rule of gas turbine blade when friction was increased. So you imagine you're increasing friction, you're expecting to have less motion, less failure. It was happening the opposite. So this is a complex problem. It's multi-scale, multi-physics, but we didn't even understand the fundamental. And to really tackle this problem, we went full on backwards in a way. We wanted to have some solution that was applicable in practice, and we wanted to go towards a real-time monitoring of the friction force evolution. But to do so, we have to go through steps, and I'll walk you through these steps. The first one was, do we understand even the simplest model of friction? Can we develop a model? Can we validate this model with experiments to really understand what is happening? Can we then develop more complex models to investigate useful features that are robust to changes? And then can we develop advanced models that integrate what we know from physics with the measurements, with the data and the information? So during this talk, I will walk you through these 4 steps. So let me start with the most simple thing that you can think of. There is a single degrees of freedom. So there is a mass, there is a spring, and we are activating the base motion. And what you can see are 2 types of degrees of freedom. In panel A, you see basically a degrees of freedom in which the mass is in contact with the wall. In panel B, instead, you see the base and the wall that are joined together and they move up and down. And the mass is still in contact with the wall, but the base and the wall move together. What we did was looking back at what Denarto did in 1930s. And it was developing some analytical expression of transmissibility of the base motion. And what we did was actually extending this technique to actually observe what you see here to the left. There is the displacement transmissibility versus the frequency ratio for the 2 types of system, and being able to define in this panel at the bottom, to the left and to the right, some interesting region. These regions are regions in which the mass will not move, fully sticking. The mass is actually moving always, continuous motion, or there is stick slip. And stick slip, as I was telling you, is very important. It means that we are stopping and moving, and this can affect the remaining useful life of a structure. So being able to understand which region we are, depending on how we are driving the system and the friction force present, is very important in engineering. Okay. So we understood this from the numerical point of view, and what we saw was something that was very, very interesting and unexpected. If you look at this figure here, top right, you see that there is an inversion in the color of the curves. So before the blue was on top, and now the blue is at the bottom. And you can see also that this is happening on reverse. And it happens at this sort of what you can call a magic point. What is happening there is something that was sort of unexpected, because it's saying that you increase friction, and instead of reduce motion, you're actually amplifying it. So this is interesting. Is this then the cause of failure? It might be, but we really wanted to understand if this is physically possible. Is this just a mathematical model issue or a numerical problem? And what we did then was investigating basically the behavior of the system. And just for those of you that are not familiar with stick slip, what it means. To the left, you have a base motion, a full cycle of harmonic motion, and you see the mass how it is moving. To the right, you see the same, but there is stick slip. And you can see that at some point in displacement, we are actually not moving, and then we go and move again. Okay, so you can see the two stops within one cycle. If we think about velocity, how does it look like? It looks more complex. Again, the mass motion is in red, the mass motion is in blue, and the continuous motion versus the steady state to the right for two stops. Okay, so what is the challenge there? Well, we understand that the stick slip can have an impact, but if we even look at the numerical problem, just not even going to experiments, but really validating the analytical results that I show you, what is happening is that we see that the accuracy of the numerical problem for this simple single degrees of freedom may actually be poor. And this is because it's a stiff problem and we might need specialized numerical solver and standardized integration technique with explicit event condition. Okay, so even from analytical numerical point of view, this seems very complex. How can we go back to physics-informed machine learning if we don't understand this? And before doing that, do we understand if this is happening experimentally? So what we did was developing a setup in which you see basically a base plate that is moving. This is the mass, that is the mass of our single degrees of freedom that is in contact here. And what we are doing is that we are exciting basically the base. This is moving and is in contact with the friction contact, and this is creating friction to the system and might lead to this type of motion. Now, you're going to see in this video, first continuous motion, but then you're going to see the effect of stick slip and of different type of stick slip. You can see when basically the mass, again, there is the top plate, is actually stopping and then moving. And within a cycle of base motion, many times it is stopping, even to the point of 12 stop stick cycle. Sorry, 12 stops within a cycle. Okay, so what we did, as I told you, for us, it was very important to validate if this phenomena was correct. And actually, we were able to validate that this is true. So it was not just coming from the analytical solution. It was not just a numerical artifact. It was there. And experimentally, we proved that. This is telling us something important when we monitor structure, that we have to be careful for this inversion point, but also that we really have to understand in-depth physics. And of course, this was for a single degrees of freedom and everything was idealized. What if we consider other forms of damping? Can we actually learn something about the feature, the robust feature? And we introduced basically a more complex friction damping model in which we consider different static and kinetic friction coefficient, and we included modal damping. And what we developed as a key understanding was that the behavior was not affected much by other system damping. And then we were like, okay, but we know the friction might not be, just a Coulomb friction, just a constant value, or different static and kinetic. It might be more complex. Will that friction variation, the fact that we have a different model depending on the two materials in contact, affect the behavior? Can we still learn something? Do we still have some robust features? And what we did was investigating the Hammond-Coulomb friction law with the rate state friction law that are shown here. And what we did see by doing an optimization is the following. So imagine that we have two different laws. One is the steady state version of the rate state model, and the other one is the Hamilton-Coulomb, in which we have static and kinetic friction coefficients that are different. We say that what is true, so it's a numerical simulation. We say that what is true is actually the DR, and we want to find a pair of static and kinetic friction coefficients so that we can go back to these results that is shown here, that is telling you mass displacement versus forcing. We would like to get basically this plot. And what you see are the parameters of this DER law, this Fredestein law. And what is interesting is that you can see that only in some region, the friction law will not matter, while there are many regions in which it matters. And what you see here are these effects, and every time here we have stops. In the DR, when we are actually looking at our model, we have a big difference. So this is very interesting because what this is telling is that if we are in a parameter space in which we are basically our friction model is in some parameters, we basically might be fitting a completely wrong law. And therefore we might have completely wrong results, especially if we are dealing with stick slip and multi-stop. So this was leading us to think, okay, we need to have a more robust features. And again, we are trying to come from the physics point of view before going into the machine learning. And what we realized was that the most robust feature is actually this friction force versus velocity, which is great to know, but then it's like, how are we going to get it? How do we obtain this friction force versus velocity graph from experiments? And how do we get back to it? And our strategy is actually to use everything that we learn from physics to inform some machine learning strategies. And that's what I'm going to tell you now. So apologies for this diversion into physics and to stick strip, but I think that is always very important to talk about the physics before going into the strategy of the machine learning. Okay, so I'm going to present to you just two of the strategy, although there were more that have been developed. And the first strategy is basically focusing on saying, we want to figure out how we get back to the nonlinear equation, because we have Coulomb friction in this case, and we know there is going to be a nonlinear equation. So in general, if you have a system of equations that can be written like this, you may have a functional form relationship that is unknown and a bias. And a part of the equation is something that you know. So for instance, you may know the mass, you may know the stiffness, but you might not know the friction. So what we can do there is to actually leverage on what is called the RK4 SINDI. And basically, we want to take time series noise and sparsely collect measurements. And what we want to get out of that is an approximation of the functional form that we don't know. But we want to have this functional form approximation to satisfy certain criteria. And this criteria is that actually it must satisfy an integration, the Runge-Kutta scheme. There is something that we knew that was important already from the numerical point of view, because we knew from physics that that was important for this type of problem, and will help us actually reduce the number of functions that might satisfy this approximation. And the way in which we want to build this approximation, this FK, how do we approximate that, is to consider some sparse coefficient that can be obtained by this optimization, but also a library of candidate of functions, basically, that are user specified. So again, they depend on the physics knowledge. Okay, so this looks great, but we always have to remember that every measurement can be fitted very well with just with polynomials. And we then fail to go back and get our governing equation. And the governing equation will be generalizable only if we select the correct candidate function. Okay, so what did we do? We took the experimental setup that we had before, from which we learn a lot, and we said, okay, in general, the governing equation in the state space form can be written as they are written here. Great. What we can say is that we have available the measurements of the displacement of the top plate, but also the base plate. We know both. And we have some inductive bias because we can assume that we know already what is, for instance, the damping coefficient, the natural frequency, and even the friction value. That's okay. But what we would like to know is actually the governing equation, the shape. And what we're going to do is to select some candidate function. We might assume that this is coming, from friction, but we might have some polynomials, some sine and some cosine function included. And we're going to consider three cases. And I think that this is very important to show these cases because I highlight something that sometimes we might forget. So the three cases are focusing on having measurements from the base excitation. So we know the input to our system. In the second case, we don't have the base excitation, and it's actually data-driven. We are gonna basically infer. The third case is the one in which we say we have a perfect harmonic base excitation. It's actually from physics because it's never going to be perfect because it's a real system. So it's never going to be a sine wave or a cosine wave, a perfect one. Okay, so what you see here are the results, and I'm going to walk you through them. So you see here the displacement and the velocity as a function of time. And what you see here is what is happening in terms, again, when we have measurement of the excitation. If we assume that we have no base excitation and we have do data-driven, and actually what happens if we have perfect harmonic base excitation. And you can see the comparison with the ground truth and with the measurements. Now, the thing that immediately strikes everyone, of course, is the green curve, because there is no base excitation, it's data-driven, and we have very, very poor convergence. Why this? Well, I told you that we were using in our, basically, dictionary, only first-order polynomial. If we use better polynomial, we will have a better fit, but there will be a fit, and it will be something that will be unphysical. And then if we use a perfect harmonic excitation, actually, we still get something good in terms of the results. But now let's look at the equations. So at the bottom of the slides, you have the equation, you see a ground truth, and then you see what is happening in case A, B, and C. And you can see that if we include the measurement of the excitation, we are actually able to reconstruct very well the governing equation. But if we don't do so, and we have no base excitation, and we build it by using the wrong candidate of function, basically, we will get something that might look good in terms of the results because it's fitting, but it's not the governing equation. And similarly, if you assume that the input was perfect. So again, we have to be very careful in engineering because most of the time we make some assumption, but we have to be careful about what this will mean if we use then a physics-informed machine learning tool. And of course, we needed to extend this for stick slip because the results that I'm showing you are very beautiful and they are just continuous motion. So what happens if we have stick slip? What happens is that stick slip make the problem even more complex, and we cannot use even with this physics bias. We have to do something more. And we have to use some explicit event condition actually to be able to characterize this. And what we did was basically, again, using some inductive bias and focusing on the friction term that we want to learn. So we want to learn both the coefficient and the signium function. And with this time, we were kind enough to give also second order polynomial signium and the x and y. And actually, if we look at now the response, then now you're expert with, this is the displacement and this is the velocity. So you see that there is 2 stops basically per cycle. And what you see here is that our measurements compared to the ground truth and the arc forcing are actually performing very well, both in terms of velocity and displacement. And we are able to characterize the response. And actually, if we think about the term that we didn't know, in this case, and again, we were using also both the input base and the top line measurement. If we think about what we wanted to achieve, actually, we were able to reconstruct perfectly the function, considering this is the ground truth. But there's something missing, and it is the uncertainty quantification. We are actually able to reconstruct the equation, but we are able to basically get a governing equation that is deterministic. It's not accounting for the fact that we might have uncertainties coming from the measurements, uncertainty coming from maybe the lack of knowledge of some other parameters of some of the physics. So that's why, and we are of course assuming that there is one friction model. That's why then we started thinking about a different approach, and another approach that is the one that I'm going to talk to you now. And this approach is what is called the Gaussian process latent force model. So let's remember ourselves, what are we trying to do? In this case, we want to investigate directly and want to evaluate this force velocity curve, because we know that if we get that from physics, we are able basically to then take that information, put it in whatever model, and now we have the true force velocity relationship. So how do we do that? We partially know the physics of the model. We have some basically equations that govern a system. We have some measurements, and we have some input measurements too. We assume that we have that because we know that if we don't, that might be very wrong and might lead to wrong results, as I showed you also earlier. And what we do is that we want to model what we don't know, the friction force, to which we assume that we don't know even the functional shape. We basically say, okay, we want to use a Gaussian process. So what do we do with that? So basically, we consider, again, the most simple case study so that we can understand it. And it is a single degrees of freedom with the mass M, with the damping C, stiffness K. And then we have a force that is basically our unknown latent force. That is the friction force acting on the system. And this is the input that we assume that we know. And if we use the Gaussian process latent force model as it is, the state-of-the-art Gaussian process, what we will get is actually a very good approximation of the nonlinear force, all things considered, but we are gonna basically miss the edges. We're gonna miss describing the stick slip. And if you think about what happened in reality when we look at the nonlinear force versus velocity, is that we are not able to estimate correctly the sharp edges. And it makes sense because it's a Gaussian process and it's difficult to actually build this smoothed sharp variation. And the main challenge here is that, again, if we want to use this in engineering, with this, we will get an incorrect friction force description, especially when the velocity is closer to 0. And that's actually when we need to know even more what is happening. So what we did was using a Gaussian process. So for those of you that are not familiar with that, I'm going to just give a brief overview. So imagine they have a function f of t, and t is the variable that is changing, and we want to approximate actually as discrete. So at every point, we will get basically a measurement, or we might not. And what we can say is that if we know the response at that point, then we have an actual value. Otherwise, we will not know what is happening at that point. And what we can say is that if we don't know, at each point in which we have no knowledge, we can put a Gaussian random variable. Now, the collection of Gaussian random variables at any point is actually a Gaussian process. And what this helps us doing is the following. If we have this function blocked in two parts as observation f0 and things that we want to predict f star, now we are able to say that given a training data set that collect the measurements of the force at that t0, we can now predict what is happening at f star. And actually how this is done is very, very efficiently, because with the Gaussian process regression model, basically we get almost for free what is the predictive mean and variance. And basically what we can incorporate with that are the information that comes from the data and the uncertainty in the measurements that can be noisy or otherwise. But we also can incorporate the prior knowledge of what it will happen between 2 points of the response. So if we have some information about the smoothness of the response function. And of course, we can also embed the prior mean function. So basically, what can happen is that we're going to have, from the data that we know that we observe, we will have some deterministic points. When we don't know, we're going to have prediction. And again, it's like cutting at every section here and having a Gaussian distribution with the mean and with the variance. And depending on where we compare to the measurements that we have, we will have a different confidence, a different uncertainty on it. Okay, so this was a sort of crash course on GP, just giving you the least amount of information to understand what is happening. But the idea is that the GP is not enough to treat this type of problem. We need a switching Gaussian process. And the reason why we need a switching is that we know that we have some stick-slip behavior. So we don't have a continuous motion. And the switching models actually relates to 3 phases. One is the sliding, so when the system is moving. The other one is when we have the stopping, so the sticking. But also we have a resetting model that we have to take into account because we're going to have discontinuities in the latent friction force. And what we do is basically applying the switching latent force model by using a linear Gaussian state space model. Without going into many details, because I can refer you back to the paper, how does it work? So the idea is that we have noisy measurements, we have driving force measurements, and we have the system parameters, some of them that we know. And what we want to do is to set some initial information. So we have to set up which is the kernel function, and we have to talk about basically the latent force model and how many latent force model we're going to combine, and the number of Gaussian that we're going to actually use in the assumed density filtering and the expectation correction algorithm. And the switching Gaussian process latent force model actually take then these blocks that you see here, in which first we do this hyperparameter estimation, and then we do this expectation correction. If we do so, then we are able to estimate the posterior. Okay, so how does it work? How does it look if we apply to experiments? Because that's what we care about. Again, we are not measuring friction directly, we are looking just at displacement. And from that, we want to retrieve the friction law that we don't know. And we just assume that we have a Gaussian process there. So can we actually go back by using a switching Gaussian model, switching a Gaussian process latent force model? And what you can see here are the displacement, the velocity, the acceleration, the friction force, and the model when we are switching between these 3 models, the sticking, the sliding, and the reset model. And what you see here is the friction force versus velocity compared to the measurements point that we have. And you can see that we are finally able to characterize the sharp edges and to basically understand better the friction law. Now we can take this friction law and we can use it in different models, and we can actually have better engineering models to make prediction. And of course, this is great, but works only, there's a disclaimer, it works only for one type of nonlinearity. And because there is the Gaussian process inside, there are some dimensionality issues that need to be tackled. So what I tried to show to you in the second part of the presentation was the thought process of using physics-informed machine learning to get towards a real-time monitoring of the friction force evolution. And I told you first which were the most important physical relevant physics parts that we wanted to incorporate, that we wanted to validate those. Then we wanted to understand if we can build a more complex model. And we then wanted to be able to incorporate what we knew with the data-driven approach. But of course, there is much more that needs to be done. And there are multi-physics, multi-scale problems, the question of where to measure what and when in engineering structures, and the fact that we may have multiple nonlinearities. And of course, again, different physics and for machine learning might return different behavior and different kind of information. So what do we trust? We want to characterize uncertainties, but also we would like to incorporate information that comes from different sources that might be of different quality. And it's always important to remember that although we want to include physics, if the physics is wrong, if we are going to put a wrong constituent model, then everything else will be wrong. So this is another thing that we have to remember. We have to develop techniques for removing inappropriate physics bias as well as data bias if we have corrupted data. Okay. So there is a global push to address all of these challenges. And within the DVU group, actually, we're working on other physics-informed machine learning problem. And I'm not going to go through that because, again, I can see Zach's face and he's getting nervous. But there are just two things that I wanted to say. The first one is this very nice work that is led by Yang Hun. You can see his picture there, in which he's been developing a technique to account for spatial and temporal correlation when we use statistical machine learning for engineering application. And you will see in this paper how important it is to account for this correlation and how much it will affect the prediction of the posterior distribution of the uncertain parameter. So this is something very important, especially because we are going towards having more and more measurements very close in time and in space. Another very interesting work that has been led by Joanna Zhu is actually about virtual sensing via Gaussian process latent force model. And this has been applied to a wind turbine. And it's for the first time that basically there has been a validation of this type of technique for evaluating the subsoil strain response in monopile offshore wind turbine. Again, I would like to refer you to this paper to see the details of this fantastic work that these guys have been leading. And you will find more on the DVU group website. And with this, I'm very happy to close this seminar and to thank you for all the attention. To remind you that more information on the website, and the work that I presented was heavily influenced by Luca Marino and Christos Lotarakis, but also because Zach is organizing with me this special issue for data-centric engineering, I would like to invite all of you to consider submitting a paper, a contribution for the work that you've been doing on physics enhancing machine learning in applied solid mechanics. And thank you very much.
Thank you very much, Alice. Thanks for that very comprehensive presentation. And before saying anything, I would like to open the floor to questions. We still have 7 minutes. So if you have any questions, feel free to ask in person or via the chat. Also, thank you for advertising the call for papers. That's fantastic. One thing that in particular that is sort of caught my attention definitely is when you specified, I think it was second example, that you might fit a model, but it might fit, but it doesn't mean it's capturing the governing equations. And I think that is really important because in the typical black box approach, we assume because it's fitting by that metric that we have a good model, and this is really not always the case. And so we definitely need to develop methodologies, that can. This actually redefines what validation of a model is.
Exactly. Right? Yes, and I think that that's exactly one of the main issues that we don't have at the moment, and we really have to define this validation because we're going to have otherwise difficulties in trusting this model in region in which we haven't observed the data, basically, or even the same region, but with slightly different parameters, honestly.
Yeah, and I think we kind of need methods of developing metrics that measure distances between how far off you are from the governing state space,
Yes.
And
if I may go back,
of course.
I think that you're completely right, and this goes exactly in defining these metrics, but also in which space this metric do exist in a way, because these metrics should be assessing the information quality, but should also assess how we compare the different, how we define the good performance in a way. Is it because we can predict if it is because we can overfit, basically, or is because we can predict then outside the range that we have observed, but how then we quantify that, and do we need uncertainties? And if we need uncertainties, when we go into the space in which we define the metrics, how do we then compare the two? So I think that those are indeed some of the biggest challenges.
There, yes. Also, another one for me is how to quantify, or how to decide on how much physics, in very simple terms, you need. Because putting too much physics is not necessarily, incorporating too much physics is not necessarily always a good thing. And so, again, developing metrics sort of that allow one to, to determine the inductive biases. This is, I think, these are all really, really important questions that now this field is kind of developing. They have to start to be asked, as opposed to kind of continue, we don't want to take down the black box route again, but we want to ask the right questions and cater methodologies around these challenges.
Yes, and going back to exactly what you say, assuming so much physics, I mean, I hope that the example that I was giving from Christos was also helping in highlighting that. We may assume that we knew that the base motion was harmonic, but actually in reality it's never exactly harmonic. If we assume the wrong physics, the bias will lead us to a wrong model at the end. So really, indeed, what you said, that we have to understand how much physics we want to incorporate, and in a way, having really this data bias and the physics bias, and understand the trade-off of having both, it's extremely important. I fully agree with you.
An interesting direction, I think, that could help contribute towards these answers, particularly this we discuss now, is geometric approaches when it comes to manifolds. And there is a very promising area, and I would love to talk about this more openly at some point. And this is an area hopefully I'm also taking in soon. But yeah, this is definitely one way potentially to measure these distances, and also help us determine, in this case, how much physics we actually need. I know I'm trivializing it in the way I'm but yeah, for lack of better words. Okay, if there is any questions, your presentation was so comprehensive and very, very clear. So I think you've covered everyone's questions already. We have one question from Armin. He says, in slide 33, can you please show the candidate functions? There was a cosine with 5 frequency.
Yes.
How did you find it? Is this your final solution? And I could not see it.
Yes, I'm going to go back to the slide. Thank you so much, Armin, for asking the question. So what we did there was, let me go back to slide 33. Okay, so you can see my screen, right? Yes. So slide 33 is this one, but I think that it was slide 34 because it's the application. So basically, we say that our library of candidate function is using basically first order polynomial, sine function, and cosine of 5 frequency. And the question is, why there was the cosine with 5 frequency? The reason is that we are, in this case, we were also including the case in which we might not know which is the driving force, basically. And because we were assuming that was harmonic, then we were considering the fact that we might be driving at different frequencies. So we decided to select, based on physics, experience, and knowledge, so domain knowledge, to use 5 different frequencies. They were around the one that we thought that was correct. And again, this is one of the biggest challenges when we want to incorporate physics. In a way, we should know already in advance what is happening. So, and that's what we did this. Is it in my final solution? I couldn't see it. That's a very good question. So when we were having the cosine of the 5 frequency, basically you can see here in the case in which basically actually we are assuming that it's a perfect harmonic base excitation, that cosine and the frequency start to appearing, while they will not appear in others, because in the other function, that is not selected as a candidate function. Probably I should have explained better this part. So the beautifulness of this method is that basically you are determining this coefficient that will tell you if that you can put many candidate functions, but some of them will be dropped because they are not needed. And so by doing this optimization here, it will be selecting which candidate function will remain. So in that case, only for case B and C, the way remaining, and these are the two functions. So I hope that this answers your question and clarify the doubts. Let me know, if this is the case.
Just 1 second, I'm trying to get the audio. The audio.
Yes.
Okay. Did you want to ask a question? Okay, I guess I'll move on. There's another question from Hussein.
Yes.
Can the uncertainty technique be applied in the frequency domain data instead of time response?
Yeah, so the uncertainty technique indeed can be also applied in general in the frequency domain. It's the GPLFM that I showed to you doesn't directly lead to that. There will be some modification because the GPLFM was also built in the state space form. But what we can do independently of the uncertainties, indeed, most of the time, actually, we go into the frequency domain because then it's less computationally expensive. And there, within the group, we actually work with Filippo Giunta, that is also here, on basically propagating uncertainties by using Bayesian optimization, by exploiting Bayesian optimization for the forward problem. But also in the inverse problem, most of the time when we have time domain features, we try to take robust feature in the frequency domain to actually then do our updating. And this is the work that we've been doing with Adolphus and Eduardo Patelli, for instance. And again, you can find more information on the website, but if you have more detailed questions, please do not be shy, ask away.
Unfortunately, I will have to end the call because I have to vacate the room I'm in.
Okay.
That's all right. As Alice said, if there's any further questions, feel free to contact either myself, Davor, or Alice herself directly. I would like to say thank you, Alice, for joining us and for sharing your work. Really appreciate it.
Thank you.
And thanks everyone for joining, and hope to see you in the next seminar in 2 weeks' time. But you will receive my usual email. So thank you, everyone.
Thank you. Thank you so much, and thank you all for attending.
Thank you, Alice.
Yeah, look forward to hear from you. Bye-bye.
Thank you. Bye.